Okay, welcome to the CCRMA DSP seminar on a nice Friday afternoon at 3:30. We have Christian Steinmetz from Queen Mary University in London talking about some really interesting research on style transfer of audio effects with differentiable signal processing. We've been following this area with great interest, and we're really thrilled to hear this today. So Christian, please take it away.
Yeah, thank you so much for having me. It's really great to be here and to have the opportunity to speak about our work. So Julia said, my name is Christian Steinmetz, and I'm going to talk to you about a recent paper that we published in the Journal of the Audio Engineering Society. And this was work alongside my collaborators, Nick Bryan of Adobe, and my PhD advisor, Josh Rice at Queen Mary University of London. Just to give a little bit of background about myself, I'm currently doing my PhD at Queen Mary, and in this PhD program they have called AIM, which is AI and music. And before that, I did my master's at UPF in Barcelona and studied my bachelor in electrical engineering and audio tech at Clemson University. I've had the opportunity to do a number of internships, including working at Adobe, where I did the work that I'm going to talk about today. And beyond my work in the research field, I also have worked as a mixing and mastering and producer, doing mixing and mastering and production for a number of different musical groups. And that's kind of been a large inspiration for a lot of my research. And I think you'll see some flavors of that today in this work. The major motivation from a high level for what we're going to talk about is the reality that more people are creating audio content today than kind of ever before. And that is true across kind of audio first applications like music and podcasts, but also in multimodal or video domains, right? Like short form content or places like YouTube, where people, where audio plays a significant role as well. And as a result, there's really a increasing demand for high quality audio, as anyone creating content wants to kind of elevate the quality of their content as much as possible, with audio being an important component. Traditionally, to make a high quality recording, you might have needed a recording studio with a bunch of expensive gear, things like condenser microphones. But a lot of that has changed these days, and you can capture really great recordings, right, from almost anywhere using just a laptop computer, a DAW, and some USB condenser microphone, for example. But one of the important things to note is that making a high quality audio production doesn't really end at the capture phase. And instead, we need to consider things like audio effects and plugins, potentially mixing multiple different recordings together to create some balance, whether in the context of podcasts or multi-track mixes of music. And as I'm sure you're aware, there's many different DAWs that you can choose from, each which have kind of exceedingly high levels of complexity to create kind of a final production. And so as a result, I think kind of producing high quality audio still requires quite a bit of expertise on the part of the user. And part of the motivation of our work is to try to lower that barrier so that people can create high quality content for different applications with less knowledge or expertise in that case. And to switch back over to the research side, we've seen a lot of really exciting and interesting applications in deep learning for audio processing that kind of follow this kind of similar paradigm of take some large neural network and train it with some data set to map some audio, whether in the time domain or in the frequency domain, and map it to some output audio in some other space. So for example, things like music and speech source separation, speech enhancement, and even tasks like audio effect modeling. But what we notice about this framework and the tasks that we aim to solve is that kind of audio engineers are already solving this problem of creating produced sounds or shaping the style or the timbre of recordings using DSP. They don't need a neural network to solve that problem potentially. And so that could be things like controlling audio effects, potentially modeling different acoustic spaces to kind of capture different vibes or change some aspects of the sound. Or in the context of multi-track recordings, creating some cohesive mixture of multiple different sources. And all of this can be achieved, using traditional signal processing tools. And that really motivates our way of attacking this problem, in which we look at building models, in this case, neural networks that learn to control DSP explicitly. And so in this framework, we can see that, instead of having our neural network directly output some audio signal. Instead, it can perform some analysis of our input and predict some control parameters that will be used to configure some set of signal processing devices, which they themselves will then carry out the processing of the audio. And this provides a number of really interesting and unique benefits. For example, as I mentioned before, we can kind of leverage all of the existing DSP tools and knowledge that are available to audio engineers today, which is a huge benefit. And at the same time, that kind of gives us this other benefit of high quality audio processing with minimal artifacts, where, kind of on the other end of the spectrum, full deep neural networks are very expressive and can carry out many tasks, but they have this kind of constant problem of adding in artifacts in ways that we can't easily figure out how to remove them. And so kind of by constraining our problem to use DSP, we kind of for free tend to get fewer artifacts in that regard. I think another big potential benefit of this approach is that by predicting control parameters, we actually get kind of some level of interpretability and additionally human understandable outputs, right? Because the parameters that the neural network is going to be predicting are things like cutoff frequencies of filters or gain levels or things like that. And this can really provide a lot of benefit because users can not only understand what the system is doing, but also kind of adjust the output to their taste if they would desire. And finally, they also enable higher efficiency as compared to kind of full large neural networks that are trendy these days, in that most DSP can run easily in real time on consumer hardware. So doing all the heavy lifting with the DSP gives us another dimension of benefit there. So now that I've kind of motivated all of those points, I want to kind of discuss about the major research questions that we were aiming to look at in this work. And I think there are kind of two main aspects that we needed to address in order to build kind of an automatic audio production system for this context. And the first is about how do we convey intention to, or kind of the goal of the user to this system such that it can do the automated task that the user wants. And given that we have that kind of interface, there's also this question of how do we incorporate DSP into kind of the existing gradient-based neural network training framework in order to facilitate learning. And we kind of investigate both of these questions in this work. So with regards to conveying intention, what we first see is that there's kind of a number of ways that this can be handled. And I would say kind of in the current paradigm with DSP, you might have some traditional control parameters, right? So some DSP designer decides that there are some certain parameters or values that should be exposed to the user. And with the user's expertise and understanding of that device, they can convey their intention by understanding how to change those parameters to achieve some certain goal. But obviously, as we expressed before, this can be challenging, particularly for complicated devices like compressors, and even considering that you might want multiple different effects together kind of increases the complexity there. So with the popularity of kind of text to image generation, you could maybe also imagine some sort of text-based system for doing this, where the user could type in some prompt and use that to configure some effects in an automatic way. And while there's been a lot of work in understanding kind of semantic controls of DSP, it still is a bit challenging because amateur users might not have the correct language to express what they really want. They might not know what the options are. And even in the case of expert users, there's still disagreement about what certain terminology means in this case. And there's also a lack of data for this kind of thing. So what we look at and propose in this paper is to look at another method of conveying intention, in this case, by example, or as we call it, style transfer. And in this case, the user provides simply a reference recording that has some elements of style or sound that they like that they want to transfer to their own recording. And in this way, the user doesn't have to know any kind of language or semantics around what they want, or they don't need to know anything about traditional control parameters. They just need to have some example that kind of incorporates or exhibits the type of sound that they want. And the other component of this work, as I mentioned, is that we need to facilitate learning in this kind of gradient-based framework of neural networks. And we can have this kind of simplistic block diagram here that describes our general application use case, where we have some deep neural network that's going to do some analysis of an input recording, and it's tasked with predicting some control parameters, P. And these control parameters are going to configure some DSP or chain of audio effects to process the same audio recording such that it outputs some signal here, Y hat, that, according to some loss function, is as close as possible to some target recording from our data set. So for example, we might have a data set of recordings from users and then produced versions of those made by experts. And then what we see here is that in order to train our deep neural network, we're going to need to backpropagate gradients through this DSP in order to get gradients for the deep neural network, kind of applying backpropagation chain rule kind of as a standard in training these networks. And unfortunately, this is a really non-trivial task, because what's in the operations inside this DSP might be very diverse. They may have recursive operations. They may not be differentiable themselves. We may not even know what's inside that box as well. So there's a lot of challenges in kind of facilitating this kind of learning, which again is something that we're going to get into a little bit more detail in this work. So now I want to kind of set up the actual framework and specific kind of tasks that we investigate in this work, which we call style transfer of audio effects. And to set that up, essentially, we imagine that there's some user that makes a recording on their phone of their voice, for example, and perhaps this is for some TikTok video or for a podcast. And they then want to apply some effects to make it sound more produced. So for example, applying a parametric EQ and a dynamic range compressor. And in order to facilitate this, they also have some reference recording from, let's say, their favorite podcast. And we then kind of design this system that will take as input both this reference recording and the user's input recording. And we have this shared weight encoder, which operates on these audio files and predicts or generates some kind of embeddings that represent the style of those recordings, which are then aggregated by this controller, which is another neural network that is trained to predict the control parameters for these different audio effects in some chain. And again, this system is trained such that kind of the output of the system matches as closely as possible to our reference recording. And that should just give you kind of a high-level view of it before I go into the details of how we facilitated this. And before we get into that, I want to give just some quick demos of what the final system we made was able to achieve. And so in this first example, we'll hear some speech recordings. And in the first recording, you'll hear that kind of like the low end is missing. It sounds quite poor. And then we have a style reference recording that's kind of like very produced and has a lot of compression and a lot of low end. And then you'll hear what happens after we pass these two recordings into the system and configure an EQ and compressor to try to make them match.
You might need to turn on original sound. We're not getting any audio right now.
Sorry, you didn't hear that?
No, we couldn't hear a thing.
Let me try to share again. Let's give this a try.
The input speech sounds like this.
Oh dear, I shall be too late.
The input speech sounds like this.
Oh dear, I shall be too late.
The target style sounds like this.
Resided in the populous kennels.
The input speech again.
Oh dear, I shall be too late.
And the stylized output.
Oh dear, I shall be too late.
So hopefully from that, you were able to get at least a little bit of idea of what the system was doing, in that the final output recording had a lot more low end and some compression applied to it to kind of match that reference recording. We also looked at looking at some music examples where we kind of treat this something similar to a mastering task. So where we put some recording into the system and use another song as a reference. And in this recording, you'll hear kind of a different problem in that the input recording has like very little high frequency content and is very kind of low heavy, whereas our reference is kind of a more balanced master essentially. And then you'll hear kind of the final system output of the system, which again is just controlling an EQ and compressor to do this transformation.
The basic input music sounds like this. The target style sounds like this. The input music again. And the stylized output.
Great. So hopefully you could again hear some aspects of what the system is doing there. And let's see. Yeah, and so now I want to get a little bit into the details of how we built the system and what we found in the process of doing so. So in order to facilitate this learning process, we devised a self-supervised training regime that would let us kind of learn to control some audio effects with this kind of style transfer setup without any kind of human labeled data. And to do that, we essentially start with some data set that contains many different recordings of any kind. They don't need to be clean or studio recordings. It could be kind of any recordings that you have. And in this case, like I mentioned, we train models both on speech and on music. And we start by doing some basic augmentation like pitch shifting or time stretching just to increase the diversity of our data set further. And then we create two different versions of this recording where the only difference is that we take some DSP chain and we randomly configure differently kind of the top branch and the lower branch of this DSP. So for example, this could be an EQ and compressor where we kind of randomize the parameters differently for the top and the bottom. And this then generates us this XI and this XR, where the top becomes the input recording and the bottom becomes the reference recording. So we're going to task the model with predicting parameters to map this input recording back to this reference recording. And we use another trick here to where we actually are going to split these recordings in time in half. So that there's an A section and a B section. And to see why we want to do this is essentially what we're going to do when we feed this to our network is feed the A section to the top branch encoder, which is looking at the input. And we're going to feed the B section of the reference to the bottom branch, which is looking at the, again, the reference recording. And the main motivation to do this is that we want to encourage the model to not rely on the fact that the content will be identical between the input and the reference, right? Because at inference time, the user is going to supply their own voice or song and use some totally different song to do this kind of style transfer approach. And the idea here is that this trick kind of enables us to force the encoder to focus on the style aspects and not directly on the content of those signals. And so given that, we then get some embedding for the input and for the reference and simply concatenate them into a larger feature vector, which then gets passed to our controller, which is another neural network, in this case, just a straightforward MLP that is tasked with predicting some control parameters P for our DSP, which in this case is some function that we've denoted here, H, that takes as input the A section of the input and is then tasked with trying to predict the A section of the reference. And since we have that ground truth information, that ground truth audio over here that we didn't show to the encoder, we can use any kind of loss function that we want, for example, like a spectral distance to compute some error. And assuming that we are using kind of this differentiable effect approach that I introduced earlier, we can then compute gradients all the way through the controller and up to in the encoders as well to kind of train the weights of all of these neural networks using an audio domain loss end to end. And so that should kind of set up a little bit the kind of big picture of how we facilitated this. But as I mentioned, another big component of this is the differentiable effects. And so I want to talk a bit about what we found there and the different methods that we investigate. So the predominant approach for facilitating this kind of differentiable signal processing is to use automatic differentiation to do so. And this idea was popularized from the paper from Engel et al. Known as DDSP. And the idea here is fairly straightforward in that you simply take your DSP and write the algorithm for it just explicitly in some autodiff framework. So something like PyTorch, TensorFlow, or perhaps JAX. And assuming that that function is differentiable and that it has well-behaved gradients, you can use these autodiff libraries to kind of automatically apply the chain rule and get the gradients to facilitate training. But this is somewhat challenging because it's very much a white box approach. We need to know what's inside this DSP in order to implement it. And it also has some additional constraints that are not traditionally constraints we have in DSP, in that it needs to run efficiently in these different frameworks, and it needs to also be differentiable, or at least differentiable enough to facilitate learning. And so as we'll see, that does present some challenges when we want to implement this in the context of audio effects. But there also are some black box approaches for facilitating differential signal processing. So one thing that we investigated, actually that was work I did in my master's, was this kind of neural proxy approach. And this is motivated largely by work in audio effect modeling or virtual analog, where there's been a lot of success in using neural networks to emulate the behavior of existing analog audio effects. So this process starts with this kind of pre-training phase in which we have some audio effect or chain of audio effects that we want to emulate. And we simply build a neural network G that tries to, that's trained in a supervised way using some data set of input-output examples, as well as the parameter values for that audio effect. And we can use kind of any architecture we want here that's appropriate for the task and simply do supervised training to build this neural network. And then in our case, what we want to do is not so much build, an emulation of this device, but it's more so that we want to then, in the training of our controller network, actually insert this pre-trained proxy network into the pipeline here. And so since G is, a continuous and differentiable function already, we can facilitate gradient computation, essentially with no extra effort. And it gets us the benefit of we don't have to actually understand or know what's inside the audio effect. We just need to have access to the black box in order to construct this proxy. And then the idea is that we can kind of train this system as we would normally and use this proxy as a proxy for the DSP to facilitate learning. But something that you would, might imagine is that we want to, at inference time, actually replace this neural network back with the original DSP. And in our previous work for my master's, we hadn't investigated that. So something that we investigated in this work was what we call the neural proxy hybrid approach. Essentially, where during training of this deep neural network, we use this neural proxy to facilitate gradient computation. But then at inference time, we swap back in the original audio effect to use the DSP during inference. And in order for this to work, we kind of need to assume that the behavior between that proxy and the real effect are sufficiently close. And so this is something that we also investigated in this work that we'll see how that turned out in the results. And finally, there's one more method that we investigated that's been proposed previously to facilitate differentiable signal processing, and that's to use gradient approximation methods. So essentially, we can use some gradient approximation to just estimate the gradients that are coming out of this DSP with respect to the parameters, which will give us a way to kind of have a fully differentiable computation graph all the way from the loss function back to the deep neural network. And the kind of idea here is that we can use something like finite differences, given any black box function that we can make measure inputs and outputs to, and that can give us some estimate of this gradient. But finite differences is pretty inefficient as the size of dimensionality of P increases. And so in this work from Marco Martinez, they looked at applying this SPSA approach, which essentially is a slightly more efficient kind of stochastic method of extension of finite differences. And in their work, they were able to show that this was able to facilitate training of control of some different black box effects. So we also considered that here in our experimentation. So again, just to recap all of that, which was a bit of information and details about differential signal processing, we kind of identified these 4 different methods for facilitating it. And one major thing we found was essentially there was no existing comparison that was unified across these different methods. So each paper that used one of these methods kind of used it on their own task and their own kind of setup. So not only were we looking to propose this kind of style transfer of audio effects task, but also in the process to perform a benchmark essentially of these different gradient-based methods in order to understand how they compared in kind of a real-world application. And I also want to mention that essentially we needed to also introduce some auto-diff effects for our use case. So as I kind of alluded to before, we consider a signal chain that consists of a parametric EQ and a compressor. And to do this in the context of the auto-diff effects, as I mentioned, we need to kind of explicitly write out the algorithms for these effects in a framework like PyTorch. And for the context of for the case of the EQ, there's already been a bit of work in trying to facilitate this. And the biggest challenge with the equalizer is that it's generally implemented with a bunch of second order section biquad filters. And these are recursive filters, and actually recursion in the context of the gradient computation is quite problematic. Not only does it potentially pose problems with stability because we need to apply the chain rule through every time step to compute gradients, but also it's just also extremely slow because we need to do those gradient computations serially. And we can't really get the full benefit of the GPU for training in that case. So the approach that we take here, inspired by a number of other papers that use a similar idea, is that we adapt something similar to the frequency sampling method to create a kind of feed-forward approximation of the IR filters that are inside this parametric EQ. And then we can simply approximate them with something akin to an FIR filter that we can, assuming that we take the input signal and transform it to the frequency domain, we can easily compute this very efficiently on GPU by just some matrix multiplication in the frequency domain. And we found that this was really effective in practice. But in the context of the compressor, there was actually not any work that we could find when we were working on this originally for trying to make a dynamic range compressor be differentiable. And in the process of trying to design a differentiable compressor, the biggest challenge we found was making the kind of recursive, recursive branching amplitude detector, which is important in giving the ballistics to the compressor. We found it difficult to essentially make this with a feed-forward approximation. And we can really only implement it with this recursion that we see here, where we essentially kind of have these first-order filters that act when one is active when the attack is active, and one that's active when the release is active. And we couldn't really find a way around this, and it was too slow and inefficient to train it kind of with the full recursive implementation. So we made the choice to simplify this with a single time constant for the attack and release, which does remove a lot of the interesting behavior of the compressor. But we found that this could be, approximated with the same method that we used for the parametric EQ, and still gave an effect that was quite close to what a compressor might sound like. But again, I think that we should underline here that this is actually one of the biggest drawbacks of this auto-diff approach, whereas, for example, the proxy methods and the gradient approximation methods, are fully black box and don't require us to kind of make these hacks in order to make it work. So as we get towards talking about the results, I want to introduce essentially the different experiments that we ran to try to understand how these different methods were performing. So we considered a number of different models, including 2 different baselines to also understand how they compared with these kind of learned gradient-based approaches for controlling DSP. So on one end of the spectrum, we considered this rule-based DSP that we designed for our task, which involves kind of a spectrum matching FIR filter. So essentially it'd be like measure the spectrum of the reference recording and design an inverse FIR filter to kind of match those spectrums. And we follow that with kind of a simple hill climbing algorithm that tries to change just threshold parameter of a compressor to make the dynamic range match between the input and the reference. On the other end of the spectrum, we considered a full neural network approach to doing this style transfer of audio effects. So it doesn't use any DSP, instead uses a conditional temporal convolutional network, which is a relatively large neural network to try to do this mapping from one style to the other fully. So that we kind of saw that as the other end of the spectrum, which would be in some sense maybe the upper bound of performance, because it's even more expressive than the DSP. And then we also considered the different gradient methods that I mentioned, including those hybrid approaches. And as I mentioned before, all of our experiments are trained using end-to-end using an audio domain loss, in this case, multi-resolution STFT. And we train models across both speech and music. And we again use the setup of a 6-band parametric EQ followed by a single band dynamic range compressor. So to evaluate our approaches, we also considered a number of different evaluation metrics, since there kind of weren't any established methods specifically for this kind of audio effect style transfer task. And our different metrics here can be kind of thought of in different ways. So the first 2 metrics that we looked at, PESC and the multi-resolution STFT error, are kind of full reference metrics that require that we have kind of matching ground truth audio to compute them. And they give us some notion of the general similarity between those audio files. But in the case of trying to evaluate kind of the more realistic case where the reference audio might contain different content, we also considered these kind of high-level acoustic features to describe how well they were kind of matching. And we looked at, in the context of kind of spectral balance, the Mel spectral distance and spectral centroid error. And in the context of dynamics, we looked at the RMS error and the LUFS error as well, to try to capture some high-level information about how those aspects were being matched by the system. So in the case of this audio production style transfer, I want to just, there were a lot of experiments in the paper and I won't have time to go through all of them, but I want to give you just kind of the high level insights of what we found with regards to the different gradient methods. So I think first, the major result that we found was that all of the methods, almost all of the methods exceeded the rule-based DSP baseline across almost all the metrics, which kind of indicates, or at least motivates further, this approach that we're doing, which is somewhat sophisticated, to kind of have a learned approach to control these effects versus the kind of standard rule-based approaches that are out there already. We found that that while the neural proxy approach that had been done previously worked okay, the hybrid approaches that we were investigating here for the first time, where we swapped the DSP back in during inference, essentially did not perform well, and were actually performing worse in some cases than the rule-based DSP. And when we looked into the results there, it was pretty clear that essentially what was happening is that the behavior of the neural proxies just wasn't close enough to the real DSP, so that we couldn't swap it back and get good results. And so I think future work is still needed there to build more accurate kind of proxies in order to facilitate that approach. We found that the gradient approximation approaches performed better than the neural proxy, but also in practice, we found that these methods struggled with instability, and it was a bit difficult to train them and needed a lot of hyperparameter tuning in order to get those models to converge. And even when they did converge, they still weren't giving the best performance out of the models here that we saw. We saw that the conditional TCNs performed very well, which is not surprising since these are expressive neural networks. And again, so we should underline there that, those methods, while they give us good scores, don't get the benefits of the DSP approaches that we were really interested in here. And essentially what we found is that the automatic differentiation approaches gave the best performance, more or less, across almost all the metrics. But again, underlying here that the major drawback of this is that these are really just approximations of the true effects and required kind of this white box design process in order to make this work in our setup. So there wasn't kind of like a clear winner that solved and checked all the boxes, but at least moving forward, it seems like the autodiff approaches are performing the best, given that you're able to develop them for the tasks that you care about. So we also wanted to investigate a bit further to kind of understand a more realistic case when we could do this kind of audio production style from recordings that contain totally different content. And to do that, we created this production style dataset/task to facilitate that. And we did this by defining 5 different kind of diverse styles that were very sonically different from each other, where we defined distributions in the parameter space for the EQ and compressor to create these styles. And so it's different than just having a fixed preset to define these, but instead actually have some kind of spectrum or range where ideally a human listening to these different styles would distinguish between them. And we were able to generate this by taking a data set of kind of clean produced audio or neutral audio as a starting point, and then essentially sampling from these different distributions, EQ and dynamic range compressor parameters, such that we could generate a data set of all of these 5 different styles, essentially, to generate a few hundred recordings from each of these. And then what this enabled us to do is then using those kind of high-level metrics that I mentioned earlier, like the Mel spectral distance, spectral centroid, RMS, and LUFS, that don't require kind of a ground truth full reference audio. We were able to then kind of measure how close these features were being matched when the reference audio came from a totally different speaker or a totally different song as compared to the input recording, which is kind of the real case that's going to happen when the user uses our system. And what we found there was pretty much mimicked what we saw in the previous experiments, in that the autodiff approaches were still outperforming almost all the methods across most metrics. The SPSA method was doing somewhat worse, but on par. And the neural proxy hybrid approaches just simply were failing at this task overall. But overall, I think we were pretty confident that, and as you hopefully heard in some of the examples earlier in the talk, that we were actually able to get pretty realistic or convincing result of style transfer of effects using these kind of non-matching input and reference recordings. And we had a few other experiments to try to understand what our models were learning with regards to audio production style. And audio representation learning has been growing a lot in recent years. And what's interesting about our task is that we're actually interested in capturing something different than traditional audio representations, which are often very focused on content. So for example, understanding who is speaking or understanding, which sound events are occurring in some recording. Whereas in our case, we actually want to be relatively agnostic to the content and instead focus on the style or the quality of the audio. And so we designed an experiment to evaluate that and compare against kind of existing state-of-the-art audio representations. So again, we used this data set that we had constructed of kind of these 5 different styles that had random parameters. And we could then use our encoder network, but freeze it after training, and then simply apply a linear classifier layer that we're going to train using some very small data set of like a few hundred recordings from these different styles. And we then would be training it on this like 5-way classification task to predict which class the recording, which style class the recording that was being listened to was coming from. And we compared this against a few other audio representations to understand. And one was a random projection of a MEL spectrogram, OpenL3, which is another popular audio representation, and CDPAM, which is a perceptually motivated audio representation. And essentially what we found is that random MEL was actually able to capture information quite well about distinguishing the different spectral based styles, but was really bad at distinguishing the difference between broadcast and neutral, where the biggest difference between them is actually the dynamics. So it was kind of indicating that this representation didn't capture information adequate for capturing the dynamics. And it was a pretty similar story for OpenL3, even worse in some case, that it couldn't even really distinguish well from these different spectral profiles or the dynamics, kind of indicating that this model was like very agnostic to the audio style and focused probably much more on the content. On the other hand, CDPAM performed better than both of those models in the case of trying to predict some of these styles, but it still failed in the case of trying to accurately represent or capture the dynamics. But what we saw for our models is that, again, our models, which were pre-trained, with the self-supervised framework, did not explicitly ever see these styles during training, was able to get almost perfect performance in this kind of simple classification task, really indicating that these representations are quite sensitive to small EQ and dynamics changes. And we did a similar experiment also on music recordings, and I found more or less the same behavior, except the fact that doing this on music recordings seems to be a bit more challenging to disentangle kind of the content and style as compared to the speech. But I think we expected that result to some degree. I think there's a lot more work to be done too in this area of understanding how to construct audio representations that are invariant to content but focus on audio. But this was an interesting first investigation in that direction. And as I start to get close to the end of the talk here, and talking about our experiments, we also investigated the computational complexity of these different approaches, which again, if you remember from the beginning of the talk, one of the main motivations of using these DSP approaches was that we could get significantly faster inference time on CPU as compared to the big neural networks. And that's pretty clear to see here that in the TCN-based approaches, those baselines that were neural networks, any of the approaches here, the neural proxy, hybrids, SPSA, and autodiff, all kind of use DSP implementations, and on CPU are many orders of magnitude faster during inference than these neural proxy, which uses the neural network, or the TCN approaches. So that really underlined kind of that we were getting this speed up benefit. That being said, we could also see that the rule-based DSP was also achieving, similar scores for inference, but didn't have the same level of interpretability or controllability or performance as we saw in the previous domains. That being said, we can see that on GPU, the inference time for the TCNs are actually like on par with these other timings. But again, we're kind of really interested in not using the GPU for inference and ideally using just CPU. And again, these are kind of just pretty rough comparisons of these methods, but I think the differences are pretty stark between the neural networks and the DSP. And yeah, so I now want to kind of summarize the major conclusions, and as I kind of begin to wrap up. As I mentioned before, the major idea here was that we were looking at kind of the first approach to do this audio effects style transfer task, where we specifically integrate these audio effects as differentiable operators, and we optimize them end to end with an audio domain loss. And to facilitate that, we introduced this self-supervised training regime that enabled automatic audio production without any kind of labeled or human created training data. And in the process of building our style transfer system, we also did this benchmark of 4 different differentiation approaches, which give, I think, a lot of insight to future work of which directions are working, where are there open questions, and how to further balance the trade-offs between these different approaches across differentiable signal processing applications. And finally, we also investigated this kind of neural neural proxy hybrid approach, even though it didn't work very well. And we also introduced what we believe to be one of the first differentiable dynamic range compressors in this setting. And I also want to leave with you some potential ideas for future directions, as I think this work is really just beginning to scratch the surface of applications that could exist in this direction. So I think the easiest extension of this work would be to extend our pipeline to consider other types of effects like reverb or distortion, which could, imagine being used to copy room acoustics or to copy guitar tone, for example, of reference recordings. And there's also been a lot of recent work from our lab at Queen Mary working on differentiable distortion and reverb as well. So it just hasn't been integrated yet into the style transfer framework. So there's a lot of papers out there that have just been coming out this year, kind of looking at differentiable effects, which could be integrated into this framework. As I mentioned before, again, I think improved methods for neural proxy and hybrid methods would be useful because, again, those kind of give us these benefits of black box approaches. But as we saw, they didn't really work yet in this setup. It would be interesting to have a method for dynamic construction of the processing chain, because here we kind of assume a fixed chain of EQ plus compressor, but having a model that could dynamically construct that would be very interesting. Also adapting it for multi-channel use case, for example, for applications of multi-track mixing. And I think maybe the ultimate goal might be some zero-shot or few-shot adaptation of the system to new audio effects. So, saying the user can provide some effects that are in their DAW, some VSTs, and say, hey, learn to control these for the style transfer task that I have for you. I think that would be a really compelling result. And I also want to mention that there's many resources available beyond the paper. We open source all of the code on GitHub for our experiments, as well as pre-trained models that you can start playing with. And there's also kind of ready to go differentiable EQ and compressors for all these different methods that we mentioned. So I think these actually have applications far beyond just the style transfer approach we looked at here. And I'm happy to facilitate anybody in using those kinds of applications in other domains. And there's also a Hugging Face Spaces demo of the pre-trained models as well, that you can upload your own audio and try out some of the pre-trained models. Yeah, and that wraps up everything I wanted to discuss about today. And thanks so much for the time to chat. Happy to answer any questions.